have already covered rules of exponents in earlier algebra class, but because they are such an integral part of working with exponential functions, this is an ideal place to review them. These are not rules to memorize. They have very easy to prove logical backing behind them. If you just think about the regular arithmetic that you're already used to doing, all the rules make sense. So it's good to go over them and to kind of view them, write them out so you become really quickly familiar with them. But do not lose sight of the very common sense logic that is associated with them. For example, a base raised to a power multiplied by that same base raised to another power is equivalent to that same base raised to the sum of the powers. For example, if I had 3 cubed, so 3 is my base, and I multiplied it by 3 to the 4th, notice 3 is still the base. 3 cubed means 3 times 3 times 3. 3 to the 4th means 3 times 3 times 3 times 3. How many 3's are actually getting multiplied? 7 of them. So notice I added 3 plus 4 and got a new exponent of 7. That's what I mean by the rules really should not be memorized. Instead, just logically picture what you're doing and they will fall into place. If I have a product and I raise that product to a power, then each individual factor gets raised to the power. So a times b to the p is equivalent to a to the p times b to the p. So for example, if I had 4 times 5 and I cubed 4 times 5, what does that mean? It means I'm taking 4 times 5 times 4 times 5 times 4 times 5, and the order that we multiply does not matter. So I could multiply the 4's together and then multiply the 5's together, and what do you know? I have 4 cubed times 5 cubed. So again, if you just look at the regular arithmetic that you're already used to doing, you can see how these rules fall out. If I have a base raised to a power and then I raise that expression to another power, I multiply the exponents together to get the base a raised to the product, p times q. Again, let's just analyze this. If I have 3 squared and I raise 3 squared to the 4th power, what does that mean? It means 3 squared times 3 squared times 3 squared times 3 squared. And if you look, we're multiplying 8 3's together. And so 2 times 4 is 8. So 3 squared to the 4th power is equivalent to 8 3's being multiplied, or 3 to the 8th power. A negative exponent is defined to be the reciprocal. And again, for all of our rules of arithmetic and algebra to work out, it again makes sense that that's the definition of what a negative exponent means. It means the reciprocal. So 3 to the minus 1 power is equivalent to 1/3. 2/3 to the minus 1 power is equivalent to the reciprocal 3/2. And note 1/3 to the minus 1 power is equivalent to 3. So notice values less than 1 raised to a negative exponent gives you a final result that is greater than 1. Values greater than 1 raised to a negative exponent gives you a result less than 1. If I have a ratio a divided by b and I raise that to a power, just like when I multiply factors together raised to a power, the individual numerator and denominator can be raised to the power. So if I have 3/4 cubed, what does 3/4 cubed mean? It means 3/4 times 3/4 times 3/4. And if you multiply those 3 fractions together, I multiply all the numerators and I get 3 cubed. I multiply all the denominators, I get 4 cubed. And so notice 3/4 cubed is equivalent to 3 cubed divided by 4 cubed. Again, just follow with the regular arithmetic that you've already been used to. If I have a base raised to a power and I divide by that same base raised to a different power, it's equivalent to the base raised to the numerator exponent minus the denominator exponent. Creates the new exponent. So for example, 3 cubed divided by 3 to the 4th. Notice the bases need to match for this rule to apply. So in the numerator, I have 3 times 3 times 3. In the denominator, 3 to the 4th is 3 times 3 times 3 times 3. And 3 of those 3's cancel out, leaving me with no 3's in the numerator and instead just the factor 1. And the denominator is one of the 3's. So 3 to the 3rd over 3 to the 4th is equivalent to 1/3, which is 3 to the minus 1. Notice the numerator power was 3, the denominator power was 4, 3 minus 4 is -1. So when I divide like bases, you can subtract the exponents to get a simplified expression. Again, you should be very familiar with these rules. So almost to the point you have them memorized, but they are not a list of rules really to memorize. They just fall out very logically from the arithmetic you are already used to doing. A couple of other comments that are worth to make that fit into the category of rules of exponents is to remind us that a base raised to the power 0 equals 1 for any base. Now, I say that with a little bit of a caveat off to the side. If the base is 0, but remember when we're dealing with exponential functions, we really don't want our base to be 0 or 1 or a negative value. But I am going to mention that 0 to the 0 is a form that's called an indeterminate form. It's called an indeterminate form due to the fact that if the expression that was causing the base to go to 0 and the expression that was causing the exponent to go to 0, if they were both heading toward 0, depending on the functions, could cause 0 to the 0 to go to infinity or to go to, any value. It might be 0, it might be 1, it might be infinity, it might be any other number depending on what functions were limiting to 0 for the base and limiting to 0 for the exponent. But that is a topic for calculus. So as an algebra student, you really should be aware that anything to the 0 power is 1, no matter what the base is. Because remember, in our class, we're really focusing on exponential functions in which the base is not 0 or 1 or a negative value. So any base we're using raised to the 0 power is going to equal 1. I also would like to remind everybody that a sum raised to a power is never equal to the individual addends in the power rate. A couple of other comments that are worthwhile mentioning under rules of exponents are the following. First of all, any base raised to the 0 power is 1. Now, I do say that with a little comment off to the side that 0 to the 0 is a form called an indeterminate form that is due to the fact that if the function that was controlling the base was heading to 0 and the function that was controlling the exponent was heading to 0, depending on what those functions were, that form could go to any value. It could also go to infinity. So if functions are controlling the base and the exponent, that is an indeterminate form. But that's a calculus topic. In our algebra class, we are dealing with exponential functions in which the base is not 0 or 1 or a negative value. So in our class, any base that we're going to have raised to the 0 power is going to equal 1. Another reminder is that any sum or difference raised to a power is not equal to the individual terms raised to that power. So a plus b to the p is not going to be equal to a to the p plus b to the p. Now, if the power is 1 or 0, again, those are exceptions, and just think about it. If the power is 1, then you kind of really don't have a power, and a plus b is going to equal a plus b. If the power is 0, we just got done saying that anything to the 0 power is 1, so that takes care of that. But any other power, a square root, a cube, a fourth. A plus b to the power does not equal a to the p plus b to the p. Again, this is easy to get a handle on. Just plug in some examples. 2 plus 3 we know is 5. 5 squared we know is 25. 25 does not equal 4 plus 9. So a plus b to a power is never going to equal the first thing to the power plus the second thing to the power, unless the power happened to be 1, or 2 or 3 happen to be, one of them happens to be 0. Then if one of them is 0, then as you could see, you're just going to get a single term raised to a power. If I take a square root is a power. And if I take the square root of a sum or a difference, it is not going to be equal to the individual square roots being added or subtracted. Example, 81 minus 16 is under that square root. 81 minus 16 is equal to 65. The square root of 65 is a little bit bigger than 8. And it is not equal to 9 minus 4. 9 minus 4 would be 5, not something a little bit bigger than 8. So again, this should be easy to get a handle on. You should not be making the mistake of accidentally applying the powers over a sum or a difference. Just plug in some example numbers. You can easily see the point that I'm making, that a plus b to a power is not equal to a to the p plus b to the p. College algebra is really a lead-in to the rest of the engineering math sequence, so the calculus sequence and classes like differential equations, etc. So here are some examples using rules of exponents that involve the types of expressions that you will run across when you get into those other classes. So again, you're learning other things in those classes, but you're supposed to go in with a foundation of already having a good understanding of basic algebra. So once you're there, you're going to be using these formulas to do other things, not learn at that point all the rules that you were supposed to learn in algebra class. So this is a good time to kind of pause and look at some of these functions and think about how the rules that we were going over apply. Earlier, we saw a formula for a stream of deposits, and in that formula were some exponents, including a base raised to a power being raised to another power. More specifically, inside the one set of parentheses, you had r raised to the n. But if you have a stream of deposits, that r is probably going to involve an exponent. The example we had in the earlier video, r was actually 1.08 to the 1/12th power, because we were depositing money every month, and there's 12 months in a year, so 1 month is 1/12th of a year. But in that set of parentheses, we're raising that expression to the power n. So the best way to clean that up is to recognize, oh, I'm going to multiply those exponents together. So 1.08 should be raised to the 1/12th times n power. And cleaning up 1/12 times n, the n will be in the numerator, the 12 will be in the denominator. So 1.08 to the 1/12th raised to the n is equivalent to 1.08 to the n over 12 power. That is an example of using the rule of exponents, where something's raised to a power and then you raise it to another power. If you look at the example below that, we have some factors, and the factors involve e raised to some powers. If I FOILed out those factors, so I multiplied first, outer, inner, last, that involves taking e to the 2x times e to the x. And if I multiply e to the 2x times e to the x, I need to use the rule of exponents, in which I have the same base being multiplied, so I add the exponents. 2x plus 1x is 3x. So when I FOIL that out and I multiply those first terms, it turns into e to the 3x. Then notice, though, that I will get minus 4 times e to the 2x. And then when I multiply the inner terms, I will get minus e to the x. And then negative 1 times negative 4 is 4. The minus 4e to the 2x minus e to the x, those are not like terms. E to the 2x is not like e to the x. I could factor in e to the x out, but what's important is do not combine them. They are separate terms, so I would just leave them at this point, and so we're going to leave that FOILed out expression as e to the 3x from using that one rule of exponents, and then minus 4 e to the 2x minus e to the x plus 4. An interesting case about factors is shown below that, in which I have a cube root of x minus a cube root of 2. And I am multiplying it by a factor that will end up simplifying down to just x minus 2. So actually, I have the factored form of a difference of cubes, but what is being cubed are cube roots. So remember, a cube root is the same as a 1/3 power, or 1/3 exponent. So first I rewrote the cube roots as their fractional powers, and then I'm carefully looking at the pattern. So notice in the second factor, I have the cube root of x squared. So that's equivalent to x to the 1/3 squared. So using that rule of exponents, I should multiply those exponents together, and that would give me x to the 2/3. The middle term, I have x to the 1/3 times x to the, or times 2 to the 1/3. I could rewrite that as 2x to the 1/3. And then the last term, cube root of 2 squared, is going to be equivalent to 2 to the 1/3 squared. So again, you can multiply the 1/3 and the 2 together to get the simplified exponent on the 2. In this case, when I multiply out those two factors, I will have opposites of the middle terms, and so the middle terms kind of all cancel out, and I am left with x to the 1/3 times x to the 2/3. Now that's an example in which you have the same base being multiplied, so you should add the exponents. 1/3 plus 2/3 is 1. So there's where my x to the first power comes from. And then similarly, you have 2 to the 1/3 times 2 to the 2/3, add those exponents, and you get 2 to the first power. So it's just an example that you could run across in other classes. You mainly should be aware that a 1/3 power times a 1/3 power is not going to give you x to the first power. It'll give you x to the 2/3 power. In order to get x to the first power, you need to have x to the 1/3 times x to the 2/3, because 1/3 plus 2/3 is how you're going to actually obtain the 1. Now, if I do have square roots, a square root is equivalent to a 1/2 power. And so when I FOIL out these factors, I will multiply 2 to the 1/2 times 2 to the 1/2. And because 1/2 plus 1/2 is 1, it does work out that 2 to the 1/2 times 2 to the 1/2 does give me 2 to the first. And again, the middle terms end up being opposites and cancel out, and then you have minus 5 to the 1/2 times 5 to the 1/2. But I should add those exponents, and a half plus a half happens to equal 1. So if you have square roots, it is true that a square root times a square root cancels to give you the base raised to the first power, but that's because a square root is a half, and 1/2 plus 1/2 happens to equal 1. Below that is an expression which could be written as it's originally expressed on the left, 9.6 e to the negative 0.2x being divided by 1 plus 4 e to the negative 2x, that expression squared. But notice the e in the numerator is raised to a negative power. the definition of a negative power is the reciprocal. So you could rewrite that with the e to the 0.2x in the denominator, and it will no longer have a negative exponent. So some people might consider that second form on the right more cleaned up because it doesn't have a negative exponent. And we were just using the definition of what a negative exponent means by rewriting the e as its reciprocal. Now, logarithmic functions also have a set of rules. They're a little less obvious than the rules of exponents. The rules of exponents are very obvious. If you actually rewrite these log expressions as exponents to, like, for example, if I have log base b, if I rewrote the expression using b as the base and the log as the exponent, you'll see why the rules of logs end up making sense, but they are a little less intuitive. So this set you may want to somewhat memorize more than the set of the rules of exponents. Not that the rules of exponents are not important, it's just they're much more logically obvious than the rules of logarithms. So you may want to practice writing out the rules of logarithms. It may help to do that with some examples like the ones we're showing here, and kind of double checking expressions on your calculator to see that you get equivalent values, or if you follow the rules correctly, you should. That sometimes is helpful too, to help you get the rule straight. So the first rule that we're going to go over is that log of any base of a product is equal to the sum of the individual logs of the factors in the product. So log base b of a times c is equal to log base b of a plus log base b of c. For example, if I have log base 10 of 10 times 100, that is equivalent to log base 10 of 10 plus log base 10 of 100. Well, think about the definition of log. Log base 10 of 10 is 1, and log base 10 of 100 is 2. 1 plus 2 is 3. But 10 times 100 is 1,000, or 10 cubed. So you could also see from the very beginning that log base 10 of 10 cubed should equal 3. So that's a very nice illustrative example of why that rule holds true. Now, if you're dividing instead of multiplying, then the expression will be log base b of a minus log base b of c, where c is the denominator. This might be a good one to check using a calculator. So log base 4 of 3 divided by 10 is approximately negative 0.86848 from my calculator using a change of base formula. If I take log base 4 of 3 and I subtract log base 4 of 10, log base 4 of 3 is 0.79248 and log base 4 of 10 is 1.66096. Their difference gives me negative 0.86848. So I can see I get the same expression, hence kind of backing up that this rule holds true. That's not really a proof, it's just kind of helping illustrate what the rule actually says. Log base b of a to the p is equivalent to p times log base b of a. So what did we do there? The power on the base plugged into the log becomes a leading coefficient. The power on the a became the leading coefficient. So log base 2 of 2 to the 4th is equal to 4. But then think about it from this point of view of the rule. Make the 4 the leading coefficient. Then 4 times log base 2 of 2 should be 4 times 1, which is equal to 4. We'll end up using this law quite a lot when we do change a base. For example, if you have base 2 and you were trying to change it into base e, when we rewrite it as base e, the exponent is x times ln of 2. Well, where that came from is we took e and we raised it to ln of 2 to the x because we know exponential e and ln cancel each other out. Well, then this rule of logs says, well, you know, that x that's on the 2, I can make it a leading coefficient. And so then the expression becomes e raised to the x times ln of 2. You'll see it written that way versus written as e to the ln of 2 to the x. You generally don't see it left in the e to the ln of 2 to the x form. Instead, you see this rule of logs applied. We've already talked about how to change log bases, but it doesn't hurt to review. So log base b of a is equivalent to log of some new base with the input plugged in as my numerator, and then that's divided by log of the new base with the old base plugged in. So log base b of a is equal to log base b of c divided by log base c of b. For example, if I have log base 2 and I want to change it into log base 10 because my calculator has a base 10 button, log base 2 of 10 is equivalent to log base 10 of 10, notice 10 is the input, divided by log base 10 of 2. 2 is the old base, and that ends up being approximately equal to 3.3219. If you're working with compound interest, you might end up with a base something like 1.075, and so log base 1.075 of 1.5 could be rewritten using the natural log. The numerator would be natural log of the input 1.5 divided by natural log of the old base, and that's approximately equal to 3.032. Because any base raised to the 0 power is 1, log of any base with 1 as the input to the log function will equal 0. Log base b of 1 equals 0 for any base. Remember, our bases are not 0 or 1 or negative. So log base 5 of 1 is 0. Log base 10 of 1 would be 0. Natural log of 1 would be 0. Again, that's because any value that is not 0 or 1 or negative raised to the 0 power will equal 1. And 0 is undefined as an input for any log function. So log base b of 0 will give you an error on your calculator, and log base b of any negative value will give you an error on your calculator. And that's because exponential functions are always positive, never 0 or negative, hence the domain of log is always positive, never 0 or negative. We're going to look at a few more practice problems. What if I had log base 2 of x plus 2 added to log base 2 of x minus 5? That would simplify to log base 2 of x plus 2 times x minus 5. And if I FOIL out the x plus 2 times x minus 5, I get x squared minus 3x minus 10. So log base 2 of x plus 2 plus log base 2 of x minus 5 is equivalent to log base 2 of x squared minus 3x minus 10. I'm using the rule of if you have the same base logs added, it's the same as a single expression of log of that same base with the two inputs multiplied together. Looking at another example, natural log of x squared minus natural log of x, if we use the rule in which when you're subtracting, you can divide the inputs and create a single log expression, that would be equivalent to natural log of x squared divided by x, and x divides into x squared, leaving me with just natural log of x. So natural log of x squared minus natural log of x simplifies down to natural log of x. Now that's assuming that x is not 0, but you cannot plug 0 into log, so it's kind of a moot point to say that. These types of expressions come up in equations that we often are trying to solve. So for example, you might be trying to solve the equation 3 equals log base 2 of x plus 2 plus log base 2 of x minus 5. And in order to solve that equation, you probably are going to rewrite the expression as we did, log base 2 of x squared minus 3x minus 10. Similarly, with the other expression, if you were trying to solve that set equal to something, it's going to be much cleaner to have it rewritten as natural log of x. Now look at this expression. We have 10 as a base of an exponential function, but it's being raised to 0.45 log base 10 of x plus 30.5. Now, if I analyze that using both rules of logs and exponents, using a rule of logs, I could take the 0.45 and raise x to that power, because there's a rule of logs that says the power on an input is equivalent to a leading coefficient, so I could just work that rule backwards and take the leading coefficient and make it the power on the x. I also have a sum in the exponent, so I could use the rule of exponents and break that up as a product, 10 to something times 10 to something else, where the two expressions were the 0.45 log base 10 and the number 30.5. So 10 to the 30.5 is some number, so I'm going to rewrite that as my leading coefficient. And then look at that other expression, 10 raised to log base 10 of something. Those are inverse functions, so they're going to cancel each other out, leaving me with the input of the log base 10, which was x to the 0.45. So 10 to the 0.45 log base 10 of x plus 30.5 simplifies down to some number, 10 to the 30.5, multiplying x to the 0.45 power. You will run across expressions like that when you are taking data that has extreme values, meaning some values are small, some values are extremely large, and you end up making either a semi-log or a log-log graph. So people doing data analytics, might run into data like that, and to make a readable graph of the data, you might log the data. That's a phrase that's used, meaning that you take the log of the data, and then when you're doing that, you work with expressions like the one that we have on the screen. Okay, what if we had natural log of e to the 0.3x plus 1 minus natural log of e to the 6x plus 2? A rule of log states that an input to a log that is raised to an exponent can be rewritten with the exponent as a leading coefficient. So I can take the 0.3x plus 1 and make it a leading coefficient of natural log of e. Same with the 6x plus 2. I can rewrite that as a product multiplying the natural log of e. Now, natural log of e ends up just equaling 1, because natural log is the inverse function of e, and e by itself is e to the first power, so natural log of e just turns into 1. So my beginning expression simplifies down to 0.3x plus 1 minus 6x plus 2, or negative 5.7x minus 1. Again, you'll run into that when you start to solve equations. In differential equations, you often are using methods that involve exponential and log functions, so these are types of expressions that you could run into in calculus and other classes beyond calculus. But our class is a preparation class for that sequence of classes. Let us keep practicing putting all these rules together. Look at this long expression. We have 1/2 times the quantity log base 10 of x minus 5 plus log base 10 of x plus 2 minus log base 10 of x squared plus 1. And if I think about my rules of logs, where I was adding log base 10 of x minus 5 and log base 10 of x plus 2, I could rewrite that as log base 10 of x minus 5 times x plus 2, which will actually give me the quadratic polynomial x squared minus 3x minus 10. And if I'm subtracting from that log base 10 of x squared plus 1, I could use the rule of logs that explains that when I'm subtracting logs, I could rewrite it as a single expression with the term that was being subtracted as the denominator of the input of the log expression. So x squared plus 1 would be in the denominator. Now the 1/2 is a leading coefficient on a log. So that rule of logs that we've been pointing out a few times, you can work backwards and take the 1/2 and make it the exponent on your input for your log. And a 1/2 power is equivalent to a square root. So the long drawn out expression that I had at the beginning is equivalent to log base 10 of the square root of x squared minus 3x minus 10 in the numerator, my x squared plus 1 in the denominator. And again, written in that final form, it is a little tighter. You can kind of see a little more crisply all that you were dealing with compared to the original expression that we had. One last example, how about if we had log base 2 of 25x cubed times y squared minus log base 2 of 5x y to the 4th. A rule of log states that when I'm subtracting separate log expressions, but they have the same base, notice both of these are base 2, I can rewrite that as a single log expression. 25x cubed minus y squared would be in the numerator, and 5x y to the 4th would be in the denominator. Now, using some of my rules of exponents, 5 divides into 25, giving me 5 in the numerator, but then the x cubed in the numerator and the x to the first power in the denominator, 3 minus 1 is 2, so I'm left with an x squared in the numerator. That x actually divides into one of the x's in the x cubed, and the y squared in the numerator divides into the y to the 4th in the denominator. But notice 2 minus 4 is negative 2, so I end up with a y squared, y to the power 2 in the denominator. So that was an example where we were definitely using both rules of logs and exponents. Well, this gave us a little bit of practice. Again, the rules of exponents, don't memorize them as completely, nonsensical rules. There's very clear logic behind them based on arithmetic you already know. The rules of logs are a little harder to see from obvious arithmetic. If you do try to rewrite expressions where you're using logs and exponents, you can then kind of see why the rules of logs end up holding true. But we will use these expressions as we go to solve equations and do other operations with exponential and logarithmic functions.